I try. If I cannot, if it doesn't work, I call you.
Okay.
Okay. Okay. Okay. Can you hear? Yeah. Can you hear me? Despite the am I screaming too much? Too much? No. Okay. Good. Okay. Very good.
Wait. I need to introduce you. I need to introduce you. Good morning, everybody. Thanks for coming back to day 2 of ES22. The morning session will be focused around topics in quantum Monte Carlo. Without further ado, let's get started. Thank you to our first speaker, Claudia Filippi from the University of Twente, who will be telling us about excited state calculations.
Thank you very much. Okay, so, well, first of all, thank you to the organizer for the invitation. It's my first live conference after 2 years. And also, I'm very glad to be here because I was always coming to this series of conferences when I was a student and a postdoc here in the States. So it brings back lots of memories. I like it. So I will discuss the work, the work we have been doing in the last many years about excited state calculations with quantum Monte Carlo. Okay, so when I started many years ago, I started doing rather large chromophores, maybe embedded in classical point charges or in DFT. And then after a while, I realized that we really needed to go back and look at a relatively small molecule to be actually able to establish QNC as a reliable method for excited states. Okay, so for excited states, if you look in the literature, already describing absorption is quite complicated. By absorption being a theoretician, we mean computing vertical excitation energy. Okay. So this is a very simple molecule, is thiophene, is a pi to pi star excitation. And what we are plotting here is the vertical excitation energy versus different techniques, okay? So all these, excuse me? I'm good, okay. These are all correlated techniques, okay? So these are multi-reference perturbation theory type of approaches, CAS-SCF, we go to CAS-PT2, NeFPT2, different flavors. This is quantum Monte Carlo, VNC, DMC with different wave functions, and these are couple cluster, an approximate model up to third order in couple cluster. Okay, for this molecule, couple cluster CC3 is actually reliable, but the whole range is actually 0.5 dV, which is large. Okay, so often you're told that time-dependent DFT has problems, but these are correlated calculations. Okay, and the spread is not nothing. Okay, and the situation is not unusual. So indeed, in recent years, there's been really a lot of benchmark studies for excited states. Really go to mostly assess absorption and fluorescence, but starting from a couple of clusters, single, double, triple, going higher, really extrapolating full CI. There is also mostly group of Pierce-François Loos and Denis Jacquemin, but also there is a paper by Cyrus Umrigar with heat bath configuration interaction, and really to establish, how high we must go to describe excited state accurately. Okay, so, and for many excitation, which are dominated by a single, so they're relatively simple excitation, it has been shown that if you're taking a couple cluster CC3, so is an approximate up to triple, you have a mean absolute error of about 0.03 V. Okay, so now if you want to convince these people that quantum Monte Carlo is an accurate method, that's the type of accuracy you should be aiming at, okay? So that's what we have been actually looking at. Okay, no, it goes forward. Okay, so excited states are quite demanding. You often have a stronger electronic correlation, so they're open shell. You need to be able to describe, multiple energy surfaces with good accuracy, with balanced accuracy. You have a wealth of phenomena, absorption, fluorescent, intersystem crossing, you're having conical intersection. And also what is nice also for us is, in some sense, a place where computing structural relaxation is quite difficult, okay? So for instance, time-dependent DFT in proximity of conical intersection will fail, and that's really a niche where you're having not many methods available and suitable for the purpose of studying, relaxation along an excited state potential energy surface. So now, here I will talk about quantum Monte Carlo, mostly real space quantum Monte Carlo. We're going to see a different flavor in a couple of talks. So why doing real space QNC? In principle, we are having a very favorable scaling. So if you're computing the energy, it would be n to the fourth with a rather large prefactor. You have a lot of flexibility in choosing your functional form of the wave function. So you can include electron-electron distancing, non-orthogonal orbital. You can really play with your wave function if you're having some good idea, okay? Of course, it is highly parallelizable. And if you're looking in the literature, we have provided as a community several quite accurate calculations for medium to large system. You will mainly find a molecule in first, second row up to 100 atoms, and that's a relatively old calculation, but quite impressive, trying to benchmark van der Waals interaction for such large system, okay? On the other hand, if you look in the literature, what you will find is mostly total energy and often in the ground state, okay? There is not much out there in QNC for excited state. So now, just for people who are not familiar, I will only explain the simplest flavor of quantum Monte Carlo, namely variation of Monte Carlo. Okay, so the idea is you're having a quantum observable, you want to compute an expectation values, and that's actually an integral. Okay, so you want to compute the energy, you sandwich your Hamiltonian with the wave function divided by the norm, and then you write it as an integral. And you collect the wave function, so you have a wave function squared divided by the wave function. And if you bring the denominator below in this box, you're having an object which is greater or equal than 0, integrates to 1, and so is a distribution function you can actually sample using classical metropolis. So what you would do a random walk in 3n dimension where n is the number of electrons, and along your walk, you would actually collect the local energy. So h psi divided by psi, okay? So, and you just compute an approximate, an estimate, with by essentially collecting the local energy along the path, okay? So that's just a trick. Is a trick to compute integrals in many dimensions, but that's actually what allows us to have a lot of freedom in the type of wave function we use, okay? Of course, you have a bias of the wave function, and usually what we do, we go beyond the variation of Monte Carlo by applying some sort of projection Monte Carlo approach, okay, where we stochastically project a better approximation starting from whatever you worked on in variation of Monte Carlo. And here we're going to use a diffusion Monte Carlo. So now quantum Monte Carlo, so why quantum Monte Carlo now for excited state? Overall, I think the quantum Monte Carlo real space QNC is in a better position it was, let's say 10 years ago. Okay, there's been lots of progress, and this is also we have been part of this process. So what we can do now also, we can compute efficient derivative of the energy with respect to many parameters, also in the presence of multi-determinant. Okay, so what I'm showing here is a bunch of system. We are going from a butadiene C4H6 to something as long as C60H62. So on this side, what I'm showing is the cost of computing the energy plus the derivative with respect to the cost of computing the energy alone if you're doing a wave function optimization, okay? So what we do is we are going from this small system to a large system. We are having a single determinant, and the number of parameters grows, and what you're having is that the relative cost, essentially plateaus and remains of the order of 3. Okay, and these are computing, derivative of the wave function with respect to the parameter, and also the application of the Hamiltonian on these derivatives. So with only a cost of 3 with respect to just computing the energy alone. So in that sense, we don't need to rely anymore on having the Beasley orbital or the whatever orbital you wish, but we can actually consistently self-consistently optimize the wave function within our approach, okay? On this side here, I'm showing the cost of computing the energy and the anti-atomic forces with respect to the cost of computing the energy alone. And here we are looking at the complexity of the wave function. We're increasing the number of determinants, and we are going from, let's say, the small molecule to the very large molecule. We are not using linearity, and we are actually keeping the cost of the order less than 3. Okay, so I'm not saying that this is cheap, but if you're willing to do a quantum Monte Carlo calculation, you can actually now, let's say, variationally optimize your wave function and also relax the structure. Relax your structure, okay? And there is also a lot of tools for optimization, and so we can really treat quantum Monte Carlo as an internally consistent theory. Okay, so now, even though it's an internally consistent theory, you still need to choose your many-body wave function, okay? You need to choose what you want to use and what you want to optimize, what you want to use to start, for instance, your diffusion Monte Carlo, okay? So typically, we are using Jastrow-Slater wave function. So we are having a Jastrow factor which contains Rij terms, so the cusp and repels the electron, and then you're actually multiplying by a summation of the determinants. Okay, so you can think about your Hartree-Fock, and then you start to excite. You're having a configuration interaction expansion, and that's the type of wave function we use. And what we hope is that in the presence of these correlated component, we can get by with fewer determinants. Now, there are many open questions for excited states, also for ground state, is whether we do really need multi-determinant, okay? Again, as I said, in the literature, often people only use one determinant. And then the question is, how do you choose this determinant? Who tells you what to include? And now, if you do a lot of work to optimize everything, do we even need to do a diffusion Monte Carlo calculation? So can we just stop at the variational level? So now, as I said, you're talking about excited state, and if you're looking in the literature, people, the chemists mainly, use a complete T-space wave function, okay? So the idea is you're having such a system, you say is a pi to pi star excitation. I consider, the two pz orbitals coming out, so I will have a 3 molecular orbital, that's a pi. 2 of them are doubly occupied, that's your virtual, and I build, all possible excitation of 4 electrons in 3 orbitals, okay? And that's gonna give me 5 determinants. Now what I do is I start to make my chain longer, so I go CN5, we'll have, 5 orbitals, 6 electrons in 5 orbitals, and I keep going. Now here I got to CN11, so 11 heavy atoms. I will have 12 electrons in 11 orbitals, and the number of determinants grows, okay? So here we are already 100,000. Now, of course, here, you are using your chemical intuition. You are only correlating very few orbitals, and maybe they're not the good ones. Maybe sigma orbitals are important. Maybe the sigma relaxation is important in the presence of the excitation. And moreover, once I go much beyond, we're going to have to start to actually chop the expansion, decide that we are going to leave something out, okay? And that's a bit arbitrary. So what we've been exploring in the last few years is to actually use a better scheme to build the determinantal expansion inside quantum Monte Carlo. And what we do is, so there's been indeed a rediscovery in the field of selected configuration interaction. Okay, so the idea, there are many flavors, but the basic idea is you're having, let's say, a small set of determinant, a space 0 from which you start, and then via the Hamiltonian, you start to actually go outside your initial set of determinant, your Hartree-Fock determinant, for instance. So you start to add more and more determinants. And now in the CIPSI flavor, what you do is you're accepting, let's say, you're including a new determinant connected to the original set based on their second order contribution to the energy, okay? So, and then what what the chemists would do, they would say, okay, very good, I have my variational energy, I expand this wave function, the space, I put more and more and more determinants, and my PT2 correction in the limit of the full CI limit will go to 0, and I can extrapolate, and I will have an exact estimate, an extrapolated estimate of my total energy, okay? And the question is, okay, here at least is automatic, I don't need chemical intuition if I don't have it, and will this give me a better, a more compact QNC expansion? Okay, very good. So now here, I'm showing you some results. To show you some results. So these are excited states in quantum Monte Carlo for a cyanide dye. So the excitation we are looking is a pi to pi star. They're actually in different symmetries. So effectively, I'm doing 2 ground state calculations. And what I'm showing the x-axis is the use of different wave functions. Okay? So the exact result, the best estimate we have is a CC3, and that's an extrapolated full CI. Okay, so that gives me kind of a boundary of where I'm supposed to actually be falling. Now, if for the ground state I use a single determinant, I could try to use for the excited state a HOMO to LUMO excitation, for instance, 2 determinants. Okay, and then I'm up here. So that's a variational Monte Carlo calculation. So something like 0.3 V off compared to the exact result. Okay, so the whole scale is 0.5. I do a diffusion Monte Carlo. Diffusion Monte Carlo helps me a lot. But, well, okay, a 0.1 EV, but that's really not enough to bring you down. Okay, so the conception that QNC is exact, well, it depends a lot also on what kind of wave function you're using. Okay, and here I'm optimizing all parameters inside the wave function. Then you can go on, you can do a CI single, actually variation Monte Carlo shoots up, but diffusion Monte Carlo cures it. Here we start to use complete lattice spaces. We include the pi orbitals, some pi sigma, more pi and sigma. And you know, the VNC sure start to go down, but I need to truncate. I'm already at 73,000 determinants. Diffusion Monte Carlo always help, but okay, it's very slow, okay? And what I'm showing here instead is using this automatic selection, which will explore very quickly a larger space. What we have is the variation and the diffusion are very close to each other, almost on top of each other. And the number of determinants I can get by is, here I'm expanding from 1,000 to 18,000, and I have very accurate results, okay? So what I'm showing you, therefore, there is a Stroud dependence, but using this smart selection, we can get compact and accurate results. So, okay, so here is just 2 different, small molecules. They're difficult for different reasons. Now the scale is going much, much more down. Okay, so now we are within chemical accuracy, 0.06 eV. And here again, we are increasing the number of determinants, is the ensemble of determinants between ground and excited stage. And we are having variation Monte Carlo, diffusion Monte Carlo, and with about, 5 to 10,000 determinants, we are within, the full CI, extrapolated full CI, and the CC3 values, okay? And again, so we can use a handful of determinants, and moreover, what we see is that if you optimize everything, diffusion Monte Carlo is actually not needed, okay? So what do we do, therefore? So to have, we looked also at more molecules to have a robust protocol when treating multiple states, because these are really total ends of different states. We are building a balanced expansion. So what we mean is we are performing a selection in such a way that the starting expansion have a similar quality. That can be the variance, the level of CI, or the total PT2 correction. Then we optimize all parameters, and what we can find a chemically accurate excitation with a few determinants. And for us, few is less than 10,000, okay? And then if you have done all this work, you actually don't need diffusion Monte Carlo. And often what we do is we are using the closeness between BNC and DNC to establish whether it actually has something sensible. Now, having a way to actually to generate balance expansion, having been able to optimize, then we can actually start to relax the geometry in the excited state. So that's formaldehyde, I think, so you're exciting it. And now the object, this molecule, will actually buckle, okay? And will relax in the excited state. So what we do is we are generating a bunch of wave functions which are, let's say, consistent in quality along different geometry and different states, and we can actually go ahead and relax molecules in the excited state. So here is some, again, small examples. So here what I'm showing is the mean absolute deviation for the bond length of three molecules which we excite and then allow to relax. Okay, so formaldehyde buckles, thioformaldehyde just lengthen, and also thiophene is actually buckling out of the plane. Okay, so what I'm showing, I'm comparing to Caspity-2. That's the only one where I have all three values, and we are comparing, with techniques which are often used in the literature to do photochemistry. Okay, so like CC2, ADC2, and CC3 is of course more costly. Okay, so variation of Monte Carlo is the red, and we are always less than an absolute deviation of 0.01 angstrom, which I think is quite accurate. Now, of course, so far I've shown you small systems. So now we have been trying to actually go to larger system. Okay, so again, we take these are toy problems. Again, this cyanine. We go from the smallest one and we actually lengthen it, and finally we start to be in a regime. We're doing a couple cluster up to third order, even though it's approximate, start to be too costly. So we don't have a reference. Okay, and indeed, here I'm taking diffusion Monte Carlo as the reference. The red is the couple cluster, so they're very close to us. And variation of Monte Carlo, as you can see, is always very close to diffusion Monte Carlo. I mean, the scale here is chemical accuracy, 0.05 eV. Okay, so, and what also we find very surprising is that often a small system are actually harder. Is not general, is actually harder than large systems. So here we are using 10,000 determinants, but we can go down to 5,000 to get a converge excitation energy. It doesn't necessarily mean that the energy themselves are converged, but we can actually convert the excitation with quite few determinants. Okay, and as I said, memory-wise, CC3 becomes too prohibitive when we are here. Okay, so now. So what we show so far is we can get, we can generate our wave function. We have a robust protocol. We can compute excitation energy and relax, but I actually haven't told you how we optimize the wave function. Okay, so you must choose a variational principle. Of course, if you are we are computing total energies, and for us the energy minimization is usually the method of choice. Okay, so if the states have different symmetry, that's easy. You're just handling, ground state essentially in their own symmetry. And if you have the same symmetry, well, for a while we did state average optimization, but now we implemented state-specific optimization with orthogonality constraint, which has been used also in different contexts, like full CI QNC, lattice models, and here in the context of real space QNC by Patak and Wagner. But now, we are doing quantum Monte Carlo. Oops. Oh, God, if it doesn't work this time. Okay, we're doing quantum Monte Carlo, so we can also play with different variational principle. We can also minimize, for instance, the variance. We know that the variance, if you're having an eigenstate, will be 0. So you're going to have multiple minima, and you should have some variance in between. And the advantage of doing variance minimization should be that we can actually do one state at a time independently. Okay, so this is one possible functional. So is the variance, but we just use omega as a, let's say, trial energy, which we modify following the average energy. Is more stable. You can also come up with different functionals. And when we found, we started again using our cyanine dye. We optimize the ground state, the excited state. They have different symmetry. The variance goes down, beautifully. And the energy, seems to converge. It doesn't converge to the lowest energy because I'm doing variance minimization instead of energy minimization. But now if I compute, at the level of variation of Monte Carlo, the excitation, they're all rather compatible. And you say, okay, fine, fantastic, so why not doing variance minimization? I do QNC, I can sample whatever, I can sample very easily this quantity and its gradient, so why not doing it, okay? But then, oh God, okay. Oh, sorry, it's really very... Okay, so what is the trouble with variance minimization? Now, in the previous slide, we are optimizing wave function with fit determinants, and now we go to a bigger wave function. Okay, so I'm optimizing the variance for the two states. The variance goes down. I'm not showing it, but what we find is that the ground state energy appears to be converging and the excited state energy keeps going up and up and up, okay? So if I do variance minimization, I seem that, you know, I'm not converging to anything, even though the minimization of the variance converges. And of course, you can compute an excitation energy, you can get whatever you want, stopping, you know, along this number of iteration in your optimization. Now, so, of course, we know that if you're having a very large expansion, if you're going the limit of exact wave functions, we should have minima. I mean, variance have minima, okay? But in here, we're using a reasonable wave function. But what we find, if you're really going to a very large number of iterations, like 3,500, that the energy is finally settling to a much higher value. Okay, so it appears that the variance minimization is actually escaping the target state, finding essentially no barrier. Also, if you reduce significantly, let's say, the error in the sampling, making longer and longer simulations. Now, to understand what's going on, we looked at a very simple wave function with 13 expansion determinants, so just times determinants. So I have 13 linear parameters. And we can move in the space of the 13 linear parameters. So we can compute the 13 eigenstate, and we can start, you know, variance minimization from each single state. So we are seeing that the variance, you know, nicely goes down as a function of optimization iteration. You know, they're all going down to the same value. And we can see also the energy, you know, it goes through all the energy eigenstates. There are some plateaus, sometimes it takes longer. But essentially what is going to the second stage. And the reason is that the lowest variance state is not always the lowest energy state. Okay, so, and apparently there, for a very complicated wave function, which is not yet sufficiently large to be close to the exact one, you'll find that, you know, the potential energy, well, it's not potential energy, but the surface of the variance is such that you're actually losing the state. And so what we do, we do usually energy minimization as much more robust. And this was quite surprising for us because, well, okay, energy variance minimization will have its own advantages. Okay, so what we do usually now, let's say what we implemented is we are minimizing the energy of a given state with orthogonality constraint to all other states, you know, lower and higher. We are optimizing in a single run, and we are exploiting correlated optimization to actually have a better cancellation of error between the different optimization in some sense, okay? Now I will show two more applications. How am I doing? Perfect, I'm finished. So, okay, so what I showed you is, so when we can reproduce couple cluster, where couple cluster is reliable, we can go to larger system where couple cluster cannot go. We optimize everything. We have a robust protocol. We optimize everything, energy minimization. We can do it. But now it would also be nice to show somewhere where couple cluster actually fails. And that's not very difficult to find. Okay, so double excitation is really a class of excitation where you really need to go to very high couple cluster level. So if you're doing CC3, CCS, D and T, full T, you will still be off. Okay, so this is tetrazine. I'm just showing you the vertical excitation energy. The whole scale is 1 eV. Couple clusters are here. And these are different multi-reference PT2, CASPT2, and FPT2, and that's Quantum Monte Carlo with different wave function going from 400 to 10,000 determinant, and it's quite stable, okay? But actually, to our surprise, these are quite difficult excitation to get. I always thought that double excitation was a Hartree-Fock, like, you know, with a hole, but they're really very strongly correlated, okay? So therefore, we also not having very good reference out there, we felt that we really need to play a bit more to be confident that we are there, okay? So this is a very simple system. I'm showing Quantum Monte Carlo, specific optimization, CPC wave function, variational diffusion, very close to each other. CC3 is 1 eV higher. Okay, and extrapolated full CI, you can do it for this guy, is actually in very good agreement with Quantum Monte Carlo. Now, this is another one, glyoxal, again, a slight deviation between VNC and DNC, but acceptable. Couple cluster is 1 EV higher, and now we are having extrapolated full CI start to be hard. Okay, so you start to be large, you get it with a 0.1 error, but we are in a reasonable, we are reasonably close. Okay, so and then at some point we start to trust QNC as the reference. Okay, here. So the next one, here I'm showing 2 excited stage. This is supposed to be difficult for couple clusters. This is supposed to be easy if you're going up to triple excitation. And what we are having is couple cluster is off for both of them by 1 EV, but also the relative energy is gotten wrong. Okay, extrapolated full CI is nearly impossible. Well, okay, you get it with a 0.4 and a 0.2 EV error, but you can actually extrapolate better the difference, and you're having, let's say, in quite good agreement with what we have. And at this point, I would say that we trust Quantum Monte Carlo as the reference. Okay, and to conclude, what we are doing now, we are really looking at using Quantum Monte Carlo forces for molecular dynamics. Okay, so now we are not crazy. We don't want to compare, to compete with DFT for ground state. We are interested in excited stage, where you can often get by with a few picoseconds, sometimes maybe hundreds of femtoseconds. But let's say using Quantum Monte Carlo forces is really non-trivial. Okay, because you're having noise. Your forces have a noise, and this corrupts your path. What happens is that even if you're doing an MV simulation, your energy will not be conserved, and your kinetic energy will grow. Okay. Furthermore, it's very, very crucial to ensure consistency between forces and potential energy surface and energy, so meaning during the optimization of the wave function. So that one can give, some funny behavior at the level of conservation of energy. And at the moment, we are exploring strategy to follow the dynamics in the excited state. What it means is that actually a VNC MD simulation. So we excite the molecule, and then we're essentially following the molecule in the excited stage, and around 80 femtoseconds, it kind of reached a basin, and we need to continue the simulation to actually converge it towards a conical intersection where you're going to have opening of a bond or buckling, a bad buckling of the molecule. Okay, but this is very much in progress. So in summary, what I show you is that we have been working hard on a QNC protocol for modeling photoexcitation. Using SelectSCI, we can compute accurate and relatively compact wave function. We can have a balanced description of multiple stage. We can get accurate excitations and geometries in the excited stage. We are moving towards large system, but of course, SelectSCI is exponential. So at some point, I will be able to include, 1,000 determinants, and that might not be enough. So this is very much okay. We're having some idea how to further compactify this CI expansion, but that's surely going to become a problem. Okay, so we can handle difficult excitation, where such as double. We are using energy minimization. As I said, variance to our surprise is not robust. And now we are exploring MD simulation with noisy forces, and that's very much in progress. And I would like to thank the people who have done the work. These 2 ladies are okay. She finished the PhD 1 year ago, Monica Dash. Alice is about to finish, Alice Kuzzocrea. They've done most of the calculation I've shown. Stuart Shepard is a postdoc working on the state-specific and double excitation. Ravindra Shinde helps with the code, and we're having 3 senior collaborators: Saverio Moroni from CISA, Anthony Semama Toulouse is our expert in SelectSCI, and Wim Brees is a local collaborator. And I want to thank you for your attention.
Thank you, Claudia, for a beautiful talk. We have time for some questions. If you raise your hand, I can bring, we'll have a mic brought over to you.
So I guess I just asked something not that relevant. Some of people who saw Anderson model, basically they also need the spectrums. So I just curious, can you basically apply this QMC to Anderson model and then compute spectral and then solve like DMFT something? Yeah.
I cannot answer about the Anderson model. I'm sorry, but no idea.
Oh, just but I guess just the green function, yeah. Just I guess you can only compute a few excited states, right? But
well, okay. So physically, most of the time, if you excite a molecule, you care about the lowest, I don't know, lowest 5, 10, okay, you're having some crossing, but yeah, sure, we are not computing 100 excited stage.
Yeah.
We are having very much a quantum chemical approach. You know, you're computing, we are not doing linear response. We are really computing a full state, full wave function, full states.
So I guess just to get a green function still hard, I guess, in the end.
To get the wave function, you mean?
Green function.
Green function.
Yeah.
You want to, oh yeah, well, okay. So, well, you can do linear response. Okay. All what I'm doing here at the end is variation of Monte Carlo.
Yeah.
Okay. So in variation of Monte Carlo, you can surely do linear response. Why not?
Yeah.
We are not doing, at the end of the day, as I said, you know, we are trying to get by with, we are using diffusion Monte Carlo more as a validation of our results, more than the actual tool. Also, the force is a variation of Monte Carlo force, and there we can compute a lot of things.
Yeah. Okay. Yeah, we can discuss more later.
Okay.
We got a question right here, Miguel.
Hi, very nice
Hello.
talk. Two-part question, very related question. So on the first one, are you doing SEF on the orbitals that you used to do CIPSE? And second part is, if you don't, what is your intuition between adding more automatic determinants through the CIPSE procedure versus doing SEF, CAS SEF with CIPSE on top of CIPSE, and so balancing the optimization of some sort of lower orbitals versus just putting more regardless of?
No, yeah, well, okay, so that's very unfortunate, but CAS is a disaster.
But you can do CAS with CIPSE,
yeah,
right?
we do at the end. What we do is not you start from the Hartree Fock. You know, if I do the double, we include, you know, for instance, a bunch of doubles inside, some singles. So we start with an S0, which is fat. And we are also starting from CAS SCF orbital, but it doesn't really matter, I can tell you. And then we do an expansion. Usually often we get natural orbit, and then we go back and we do the expansion.
So I guess the question is, how essential, when you have some significant amount of correlation, how essential do you see this
It's
self-consistency?
essential.
Okay.
It surprised me. First of all, I didn't show you for butadiene in the ground state. You know, we really went to very large CAS. You know, you include pi correlation, sigma correlation, more pi, and you think, oh my God, the energy is plateauing. You know, great. And then you do CIPSE. You go on CIPSE, and the first part of the curve is the same, and then tick, it starts to go down, and you pick. We try to analyze, but you really get, you know, very, very excited orbitals. So maybe, let's say, more than CAS SCF, maybe something more based on multi-resonance wave function, maybe valence bond plus CIPSE, maybe it would be a better, something where you put me more chemistry intuition than just a CAS. I don't know.
Okay,
so we're playing. Yeah.
We have time for maybe one more quick question if anyone has one. I'll take it as the moderator. Could you just say a little bit about the resources required to do these calculations?
Well, okay, it's expensive. We're getting, the code is getting better. I don't know. So for instance, the little more like MD simulation, so we move the ions, we optimize the wave function at every step. Maybe it's a few thousand cars of some hours. So it's not impossible, but there is a lot of getting to it. You see what I mean? Getting to know your system. Yeah, it's not cheap. So my student can consume millions of hours with no trouble, okay?
Thank you so much. Let's thank the speaker again.
We have a Zoom question. Yeah, there is a Zoom question. Yeah. Yeah, so no. So yes, so Zoom question is asking about the optimization of the variance and how we move omega. So omega is following the energy, but let's say we also really tried to block omega, okay, to really optimize, you know, blocking omega, to really forcing it to stay where it's supposed to be. But you can see that the variance, you know, is really trying to get out. It just wants to get out of this minimum. There is no barrier. It's not a question of the functional, okay? So we also use different functional, like the one suggested by Neuskeman, and we see the same behavior. Okay, hope I answered the question online. Okay, thanks.
Okay, our next speaker is Kun Chen from CCQ at the Flatiron Institute, who will tell us about something called Picasso's bull. Kun, take it away.
Hello, everyone. Okay, so in 1945, Picasso, a famous painter, so basically he performed a study of the structure of a bull, his favorite animal. So through a series of painting, Picasso managed to derive the minimum model of bull without losing the essential feature. So basically, in this talk, we will examine the physical property of valence electrons, the localized valence electrons in materials using a similar idea. Sorry, there's some problem with the slides. Okay, so basically, in general, the delocalized valence electron can be modeled with a simple Hamiltonian known as the electron gas. In this Hamiltonian, this Hamiltonian describes a bunch of electrons confined with a uniform background, and the electrons interacting with each other through a Coulomb repulsion. So it models many different systems like materials, semiconductors, warm dense matter in the inner shell of Jupiter, and molecules. But here we will start with the simplest case of electron gas problem, basically known as the uniform electron gas or the Janelian model, and it models the valence electrons in simple metal. So when we go down the energy scale, go to lower energy scale, the valence electron in simple metal is described by charged Landau molecular theory, and there are two effects. So firstly, the electrons will be renormalized to quasi-particles near the Fermi surface, and then secondly, the interaction between the electrons, namely the Coulomb interaction, will be renormalized to a screened Coulomb interaction. And the screening here actually has a twofold meaning. So firstly, the inverse square law of the Coulomb interaction will be regularized by an emergent energy length scale, basically known as the Thomas Fermi screening length. That's QTF here. And then, in addition to that, the many-body effect will generate additional prefactor to the Q square term in the Coulomb interaction. So this prefactor basically has many different names in different subfields. So for example, in material science, people call it the exchange correlation kernel. And then in many-body physics theory, people call it the Landau quasi-particle interaction. They are really the same thing in the small momentum limit. And in simple metal, this prefactor K is known is roughly proportional to the mean distance between two electrons, basically the Wegener's radius Rs. And for all the metals, we know this prefactor is roughly between 0 and 1. What does it mean is that this prefactor always suppresses the Q square dependence of the screened interaction. And as a result, the screened Coulomb interaction is more local than it's supposed to be. And so in commonly used approximations, the ab initio methods like a random phase approximation or GW approximation, usually people completely neglect this prefactor K. And then these approximations cannot capture this rich physics here. Okay, so what it means is basically in some metal like cesium, the interaction is so strong so that the K becomes -1, and this this moment dependence in the screen cooling interaction is simply completely removed by the prefect K, and the cooling interaction become perfect screened. And of course, this K can be actually can be defined for finite momentum and finite frequency, and then this momentum and frequency dependent exchange correlation kernel play a very important role in the initial methods of material science. So, for example, once we know how to parameterize this kernel for the uniform electron gas problem, then what we can derive a simple parameterization of the vortex correction, and with the vortex correction, we can plug it into the Hades equation to derive a relatively simple vortex corrected GW approximation. And this approximation compared to a standard GW approximation where the gamma is set to be 1, this vortex corrected GW approximation will give a very nice prediction, like for correlated metal, even with the self-consistency. And in addition to that, you can take this exchange correlation kernel and combine with the Khongshan solution to derive the density response function for real materials. So then you can predict dynamic charge response of real materials. So this is basically what people are using for in time-dependent density functional theory. But all these techniques rely on high quality parameterization of the exchange correlation kernel for the uniform electron gas problem. Okay, so this uniform electron gas problem has been proposed like a century ago. However, we still do not adequately understand how this kernel looks like. So then in this study, we will basically what we are going to do is the following. So we are going to find a minimal model to describe the quasi-particles, and from this minimal model, we are going to add back the details with the perturbation theory, and from the perturbation theory, we can extract the physical exchange correlation kernel, and then after we got the physical exchange correlation kernel, we can study the structure of the kernel and we can revise. Basically, we can revise this minimal model to propose a better model, and we can then we can do another perturbation theory to get even better calculation. So this is basically the similar, very similar spirit compared to Picasso's ball study. And the first minimal model we propose is basically coolant electron gas with the Yukawa interaction. So as we just mentioned, the screening here has twofold meaning. There is emergent screening lens, and then there is a prefactor. So in the first model we propose, we completely neglect this kernel K, and this of course simplifies things, and but it also lose some physics, right? So we didn't expect it to work for all parameter region. However, because this is a simple, so this is a really good starting point. And then basically, there is a standard technique developed in high energy physics called the renormalized Perignon theory. So with this theory, it is possible to add back the corrections in this model. So because we know the original model has a cooling interaction, right? It has it's divergent in small Q limit, but our renormalized interaction is a screened one. So basically, then the way to add bactions is this cooling interaction in a power series. So the leading term is just the renormalized cooling interaction. Then there will be a counter, first order counter term, second counter term, and so on. And then basically for each in the Bayer perturbation theory, in each Bayer diagram you draw, you can write down, you can perform this re-expanding. Okay, and after that you derive a renormalize diagrammatic series. So in the diagrams, all these interactions is not the Bayer cooling interaction anymore. It actually is the static screened Yukawa interaction. And then, in addition to the conventional Feynman diagrams, there will be a counter diagram like that. Okay, so these are the details you need to add back all the detailed information which is absent in your minimal theory, and then by calculating this diagrammatic series order by order to a sufficiently high order, you can, in principle, you can get a convergent result, and the convergent result will be the physical observable you want. So we use this. Of course, like the high order Feynman diagram becomes so complicated. There are tens of thousands of Feynman diagrams that have different topology. However, these Feynman diagrams actually have a simple structure. So they are really just the sum and the product of different components, like a Green's function and Yukawa interaction. And then you can translate these diagrams into a language like which machines understand. So basically the expression tree, and the following the leaves of the expression tree is basically the Green's function and the interaction, and the node as operation, the sum and the product. And this expression tree can be very fast, efficiently evaluated in a modern computer. And then basically you need to use Monte Carlo to sample the internal variables. Okay, so basically this is a diagrammatic Monte Carlo algorithm to calculate high order perturbation theory. Then in this theory we can calculate up to 6th order, and for many cases this is sufficient to obtain a controlled result with controlled accuracy. Okay, so we first use this technique to examine the static exchange correlation kernel. Basically the kernel at the 0 frequency limit and with the momentum dependence. So we calculate the spin-spin correlator of the uniform electron gas and extract the kernel through this parametrization. And we can go up to a fairly strong interaction, up to I is equal to 5. And the error bar here actually includes both statistical error from Monte Carlo and the systematic error from the different order of Feynman diagrams. So this is a controlled accuracy. And this spin channel exchange correlation kernel is basically not known before, so this will be the first result. And in principle, you can plug this kernel into a TDDFT solver to predict the dynamic spin response of real materials, but this has not yet been done yet. On the other hand, we also calculate the charge response, and the charge kernel has been calculated before with diffusive Monte Carlo, and you can see our data are consistent with the previous calculation with much better resolution. So for the charge kernel, we cannot go to very large RS because our minimum model didn't capture the perfect screening of a coolant interaction. And overall, there is a remarkable feature. So you can see this kernel, although it depends on the momentum, however, it's almost a constant up to 2kF. Okay, so this is a remarkable feature. That means the Landau quasi-partial interaction is relatively local, is quite local, up to the scale 1/kF. That's our first remarkable feature we find. And then we examine the we use the same technique to examine the frequency dependence of the kernel. So basically at zero momentum and at a large frequency. So with this kernel, in principle, you calculate the dynamic charge response of materials like the electron function. Actually in TDDFT, people so this dynamic kernel is not known before. So in TDDFT, people are using adiabatic approximation. So basically, people are assuming the dynamic kernel is just like the zero frequency kernel. However, this is not quite true because the kernel we extracted has a non-trivial feature at the intermediate momentum. Okay, so overall, there is a constant background, more or less constant background, but in addition to this constant background, there is an additional feature. So the physical consequence of this feature is not quite clear for now. So and it requires further investigation. Okay, so basically, then in addition to this non-trivial feature at a finite momentum, the kernel is again relatively flat as a function of frequency. Okay, so that's a second remarkable observation here. Okay, so then we can, in addition to the momentum and the frequency dependence, we can study how this kernel evolves with temperature. So when the temperature increases, we expect the degenerate electron gas is not becomes non-degenerate anymore above the Fermi temperature, and then in this, then we are going to enter the region for the warm dense matter, and we can calculate the temperature, the full temperature evolution of this exchange correlation kernel from essentially zero temperature to a very high temperature. Okay, so this is basically the ratio between the temperature over Fermi temperature, and you can say it will start with this black curve, which and this Q is quite large here. So the Fermi momentum is roughly here. So you can say this black curve is roughly constant within 2kF. Then this plateau does not appear until the Fermi momentum. So that means the electron gas has the third remarkable feature. So the Fermi liquid picture does not break down all the way up to the high temperature at TF. Okay, so basically combined with these three calculations, we conclude the quasi-particle interaction or the exchange correlation kernel is roughly a constant with the entire Fermi volume up to the Fermi energy. Okay, and then in addition to that, we examine the effective mass. Basically, this is one of another important lambda Fermi liquid parameter. And in theory, actually, in literature, there are all different kinds of predictions. So there some theory predict it when you increase RS, it will go up. Some theory predict it will go down. So this is because the effect in the effective mass of electron gas, there are competition between vertex crashing in the denominator and in the numerator. So if your theory unbalance this vertex correction, and then it could predict a completely different trend. So then we use our minimal theory to calculate the effective mass up to a fairly large RS, and it turns out it turns out the effective mass is just as what predicted by the G0W0 approximation is roughly negligible. Okay, it's almost negligible in the simple metal. So this basically resolves the effective mass puzzle for the electron gas. And then the last important Landau parameter is the quasi-particle weight. And our calculation is more or less consistent with the existing calculation from DMC and the VMC. And one of the remarkable feature here, basically the first remarkable feature we find is that if we calculate the momentum-dependent quasi-particle weight, you can see the weight is again almost a constant within the Fermi volume. Okay, this is entirely unexpected. Okay, so if there is one take-home message for this talk, will be the message. So basically, as we just claimed, we find the quasi-particle interaction is roughly a constant within Fermi volume. We find the quasi-particle mass is almost negligible within Fermi volume, and we find the quasi-particle weight is almost a constant within Fermi volume. So if you combine all these facts, there is you arrive at one conclusion. So all electrons within Fermi volume actually can be modeled by the same quasi-particle picture. Okay, so that means the Landau Fermi liquid theory not only holds for a thin shell near the Fermi surface. Okay, so it actually holds for the entire Fermi volume. So the charged Fermi liquid, in simple metal is very different from like a generic Fermi liquid. So because the generic Fermi liquid like helium-3, the Landau Fermi liquid theory only holds for a thin shell, but here we can really generalize that to the entire Fermi volume. Okay, so that's basically the take-home message. And from here, from this qualitative conclusion, actually, we can derive many interesting things. So one interesting thing is to revise our minimum model we proposed before, because our minimum model completely neglect the exchange correlation kernel. One of the reasons we neglect it is because the exchange correlation kernel, at the beginning, we thought the exchange correlation kernel is so complicated. Okay, so then we remove it to derive a simpler model. However, since through our calculation, we find the exchange correlation kernel is roughly a constant, then it becomes really simple to motivate more complete effective field theory. Okay, so this will be this action. How I'm doing with the time? Okay, yeah. Okay, so basically, this action compared to the minimum model we proposed before has several additional features. First, the quasi-particle, the bare electron parameter, like the bare mass, will be renormalized to a renormalized mass m star, and of course, this m star renormalization is not particularly important because we already show this is roughly within 10%. Okay, and in addition to that, the interaction has a additional feature. So this interaction now has taken this form. So you can see if you turn off the kernel K here, it goes back to the RPA interaction. But if you turn off this K, that means you turn off K here. Then this interaction cannot parameterize the physics beyond 5.3. Okay, so that's why we decided to keep this interaction. And this interaction, this kernel is as simple as a number. So there are no need to put complicated momentum and frequency dependence in this kernel. So the interaction is on one hand captures all the physics on this side and on this side. Okay. On the other hand, it's still simple enough, so you can perform like high order calculations. So the high order diagrams now comes up with again, the high order diagram comes up with counter diagrams. And what does the counter diagram do is very interesting. So for example, this diagram, you can see there is a particle pair. So this is an electron, this is a hole. And this electron hole pair is known to be a gapless excitation in the system, so it generates a large parameter. And what this counter term do is it will exactly cancel the electron hole contribution from this diagram. And it's roughly the same here. Here there is the diagram, the topology of the diagram is different. However, there is again there is a particle and a hole pair, and this particle hole pair contribution will be nicely canceled by another counter term. So diagram, there will be counter term, remove the large parameters, and in the end, the diagrammatic series will become perturbative, and you can calculate them order by order to restore the full detail of the problem. Okay, so of course this theory, the interaction here actually is retarded and momentum dependent because of the Baeyer Coulomb interaction and the Lindenhaus function here. So this effective field theory is much more difficult than the standard effective field theory in high energy, because in high energy physics, because of Lorentz invariance, all the interaction are local and just a number, but the interaction. Okay, so we call it a non-local effective field theory. The calculation of this kind of field theory is highly non-trivial. So we develop a whole package to handle this type of problem. So we call it so basically we call it the numerical effective field theory approach. We develop components to parameterize the Green's function, component to generate Feynman diagram, and the component to perform Monte Carlo integrations. And now all this technique is ready. So, so basically the study is ongoing. Okay, so because the limit of time is limited here, so I will stop here. Okay, so in the end, I would like to thank all my collaborators, Christian Hawley, Gabriel Kotler, Carl Kokkonen, Nikolai Prokofiev, Igor, James, Eugene, Baozong, and Peng Chen. Okay, so that will be my conclusion. Thank you.
Great, thank you, Kun. We have time for questions.
So I guess in these calculations, you assume the translational symmetry, but if you add some external potential, so how hard to generalize these formalisms?
Right, that's a very good question. So of course, the calculation will be much more involved. So that's the precise why we want to develop this technique. So basically, we need a very sophisticated mesh system to represent the Green's function and then perform the Monte Carlo integration. So there are no fundamental problems. But there are a lot of technical issues. We are still.
So for the current calculations, like how long it takes to get it?
So actually, the first couple of orders is very quick. Like you can perform it calculation with a PC, like a couple of minutes. But like order 5 or order 6, it takes a much longer time. But the hope is that with this renormalized interaction, and we already have evidence for that, this renormalized interaction, you do not need to go to very high order. Like even one loop give a very decent result already. Like because in material science, we usually care about accuracy level at 10%. Like this at this order, it already give you 10% accuracy. Mm-hmm. But on the other hand, this even at this one loop order, it already goes beyond the conventional GW approximation and random phase approximation.
Other questions? Sure.
I know you said this, but I just want you to say it again. It's so surprising that you would say that parameters apply over the entire bandwidth. But we know hundreds of materials where I think it's well established that's not true. So can you say a little bit more what would happen if you varied from those elements that's up on the screen right now? If you went to something more complicated like a D-state or...
You mean more complicated, like a semi-metal and a band insulator, something like this?
Right, or just any of the more correlated materials.
Right. That's a very good point, actually. So, so basically, so far our study is for a system with a large Fermi surface. Okay, like in semi-metal, there will be like a small gap near the Fermi energy, and this gap actually will enhance the kernel. So it's quite true. This kernel K develops some singular behavior below the gap energy. But on that, so basically that means this kernel cannot be as simple as a number anymore. Okay. On the other hand, the structure of the effective action is likely to hold even for semiconductor. Okay, so what I mean is you can use the same action, but replace this kernel. It's not a number anymore. It's actually probably even have a log Q divergence or something. So and then plug this like a singular kernel here. You can still derive interesting physics. So in principle, if you handle the kernel properly, you can derive the exciton physics from this effective action. I hope I addressed your question.
Okay, thank you.
Yeah, thank you.
Any other questions?
So, so your starting action S0 is basically an electron parabola with an adjusted mass, right? And then you add an interaction term, right, with the
Yes.
with the kernel in it.
Yes.
So how do you do a material with more than one band and different masses? I mean, like, is it just as trivial as changing S0, or you have to redo everything?
Right. So that's another good question. So we haven't generalized this calculation to real material yet, but in principle, this can be done. So the rough idea is like this. So basically, we all know how to do like RPA or GW for real material, right? So, and this theory, if you just turn off this kernel, it reduced to the RPA and the GW. So actually, it reduced to a specific approximation called like a linearized quasi-partial GW for real materials. And then it just means you extend the existing linear quasi-partial GW calculation with a kernel. And then you can go beyond the leading order, like what people are doing right now, by including like one loop, two loop diagrams. Okay, in principle, you can do that. So all the band, like different band problems like this, these are basically the same as what people are doing with GW approximations.
Let's take one, hopefully quick one from Wojciech. And at the same time, we'll be checking Zoom if there's questions there.
Oh, just a quick question. So if I understood correctly, you were showing those two diagrams and you were saying that you expect an exact cancellation. If I look at the diagram on the left, I will be able to recast it in terms of a vertex correction.
Yeah.
So essentially your absorption of my interacting boson. Why do I expect that to be exactly canceled?
Okay. So basically,
or let's better say, why do I expect to be that the correct solution, that it should be exactly canceled?
Yes. So by exact cancellation, what I mean is the singular contribution generated from this diagram. The singular contribution basically is a partial hole excitation contribution in this diagram will be cancelled by this guy. Okay, so just a singular contribution. After the cancellation, there are still regular contributions. The regular contributions turns out to be quite small, even at a strong interaction, like near I is equal to 5. Okay, so it's very similar to the effect field theory, like in partial physics, like in 5-4 theory. So near the quantum creative point. So the quantum only cancels out the singular, like divergent contributions. Yeah.
Okay, I'm told we have no questions on Zoom, so let's thank Koen again.
Okay, thank you.
Our last speaker of the morning session is Miguel Morales from CCQ at the Flatiron Institute, and he'll be telling us about auxiliary field quantum Monte Carlo for solids. Go ahead, Miguel.
Hello, can you hear me? Okay, so first of all, thank you for the organizers. This is my first talk after several years, so hopefully it goes smoothly. My name is Miguel Morales Silva. I am as of a year ago, more or less, at the CCQ, the Center for Computational Quantum Physics at the Flatiron Institute. And today I'm gonna talk about what I've been doing over the last few years, which is mainly essentially been focused on auxiliary field quantum Monte Carlo and the goal of pushing it towards applications of real materials. And hopefully I get to convince you in this talk that it is a very interesting idea, a very accurate method, and hopefully would become a method of choice, or at least in the tool bag of method of choices for the study of correlated materials. Before I forget, I want to acknowledge my collaborators, because I know I'm going to probably be raising at the end of the talk. Most of this work was done with Fia Malone, who's now at Google, used to be working with me for several years in Livermore, which where I were before coming to CCQ. I also want to mention John Ho Lee, who also was an essential part of this work and at the later stages. Alfredo Correa, he's an excellent scientist and an excellent software developer, whose development that we did at Livermore. And Paul Yang, who's now a postdoc at CCQ, taking over a lot of this work. In terms of what I'm going to be talking about, I'm going to focus on describing auxiliary field and essentially the steps or all the work that needs to be taken to take it from a method that is typically applied to model Hamiltonians to a method that now can handle materials in well-converged calculations. Then I'm going to describe recent developments that we've been fighting with over the last few years to make this a reality. Okay, so as some of you might know, auxiliary field is a very powerful method for correlated electron problems. It has been shown over the last few years, especially thanks to the work of the Simons collaboration, colleagues at CCQ and many other places, that when looking at highly correlated model Hamiltonians like the Hubbard model and systems with exotic low temperature physics, it's actually quite addictive. It's competitive with methods like DMRG, which we know is also one of the leading methods when we think about strong correlation. So just to semi-random plots showing results being very competitive with DMRG on the ground state properties of the Hubbard model, or even calculating superconducting properties, for example, which are quite challenging to do. I was not involved in this work. This is mainly the work that motivated me to get into this field. So there's a very long history of AFQMC in places like nuclear physics and condensed matter, but it's usually limited, or most of the work has been done in the context of model Hamiltonians, where the interactions are very compact, and essentially the definition of the problem does not require a large, complicated problem. It's usually simplified Hamiltonians. The application to real materials is a very different and challenging extension to this method, because now as I will show you in the next slide, we're talking about a drastically different Hamiltonian with a lot of technical issues and much higher computational expense. So even though the overarching goal of what I want to do over the next few years is to take AFQMC as a useful tool in the study of strongly correlated materials, to get there, we have to solve a whole lot of technical issues. And I'm going to hopefully show you that most of these have been taken care of. And we're now at a position where we can think about AFQMC as a method for materials. A very brief introduction about wave function-based quantum Monte Carlo, and thanks to Claudia, I don't have to go too much into this. This is my sort of one slide review of, by the way, that I'm specifically talking about wave function-based QMC. QMC means many things to many